motivation. Okay, so let's get started. So before I start, just a couple announcements. I think those of you who are following Piazza know that there was a lab 0 that was handed out, right? It's just a setup assignment. So make sure you accept lab 0 in GitHub and then set up your computer to run Docker and virtual machines, because that's what those are the tools you're going to use for the actual lablet work and lab work that's coming. Okay, so keep that in mind. We put a tentative deadline on it, but it's not a graded assignment. So long as you complete it, we are not really strict about when you finish it and whatnot. Okay, all right. So let's continue from where we left off last time. So we were talking about architectures for distributed systems. So that part is done. Today we are going to start a new topic, which is communication in distributed systems. Right. So this is the agenda for the class. I'll talk about message-oriented communication first. Then we'll talk about remote procedure calls. Then we'll talk a little bit about how remote procedure calls are implemented, so that you know not just how to use it, which you will in this class, but also how to design RPC system that's at the backbone of many distributed systems. Okay, so that's the agenda for today. Next time, we'll talk about remote method invocation, or RMIs, which is the RPCs in the Java world. Yeah, really are RPCs in object-oriented world. So but that's for next time. But today, let's start with message-oriented communication. So before we do that, we want to start at a very high level, which is how do you enable communication between two processes that are part of a distributed system. Okay, so assume that you have two processes that want to communicate with one another. Okay, how do you enable that communication? Okay, so there are two approaches for doing this. One is called unstructured communication, and the other is called structured communication. Okay? Unstructured communication essentially uses either shared memory or shared data structure to communicate. Okay? So for example, if you want to, let's say, send a message with a single integer to a process, okay, and you are using unstructured communication, you would essentially put that data item into a shared buffer, and then the other process would then pick it up from that buffer. Okay, so that's an example of unstructured communication. Okay, there's no laptops used in class today. Okay? All right. So the unstructured communication is going to use shared memory, shared data structures, and so on. And structured communication, which is really the focus of what we are going to use today, is basically going to use explicit messages. So if process A wanted to communicate with process B, you would make create a message and send that message over a network to the other process. The other process would receive the message, and the body of the message would contain whatever information you needed to send to the other process. Okay, so that's basically structured communication. So we will talk about the concepts of network sockets, which allow us to essentially perform this inter-process communication. They're called IPCs. Okay, and we'll also talk about higher level abstractions, which are remote procedure calls, which also allow us to do the same thing. Okay, so there is message passing can use low level abstractions like network sockets, or you can use higher level abstractions such as remote procedure invocation. And we'll talk a little bit about both. Okay, now to design your distributed system, you actually need lower level support from the operating system to enable either of these two. Okay? To do unstructured communication, the OS has to support the notion of sharing memory across processes. That's something called shared memory, okay, in the OS context. And for structured communication, you need low-level support, such as the TCP/IP protocol stack has to be supported in the OS, so that you can enable communication. Okay, so in both of these cases, you will need OS level support to enable communication. Okay. With that, I'm going to now talk a little bit about communication protocol and TCP/IP. If you have already learned this in an OS class, which hopefully many of you have, that's good. This is a refresher. But if you haven't, this is a good way to at least know the basics so that you can understand socket communication and RPCs, because everything is going to run on top of TCP/IP. So at least you need to understand what is the communication protocols and how do they work. Okay? So this picture here shows us what is called a network protocol stack. Okay? This is the net component in the OS that enables communication across machines. Okay? The network protocol stack, as you will see here, is called the OSI stack. It has 7 layers. Okay? So it uses a layered approach where you essentially have different layers or components of the network protocol stack that perform different functions. Okay? So you will essentially have these 2 columns here. This represent 2 machines on the network. Okay? The machines are not shown here. And each layer talks about a protocol. A protocol is simply rules for communication that occur at that layer of that protocol stack. Okay? So the lowest layer is called the physical layer. So there's a physical layer protocol essentially talks about how are you going to put bits on a wire, or how do you put bits into the air on a wireless channel for Wi-Fi or a cellular network, and so on. So those rules essentially form the physical layer or physical layer protocol. Okay? The data link layer sits on top of the physical layer. So this is basically where you have things like Ethernet or Wi-Fi that essentially say how are you going to send basically packets, which in this case are called frames, over the physical layer to the other end. Okay? So that's called the data link layer, sometimes also called the MAC layer. Okay? On top of that is the network layer. Okay? The TCP/IP case, so that network layer runs IP part of TCP/IP, or the Internet Protocol. Okay? That is responsible for sending packets over a multi-hop network. So it performs function called routing, because these 2 machines may not have a direct connection between them. There may be other intermediaries like routers between them. So somehow any data you sent from machine A has to make it to machine B, and that's done through the process of routing, where each intermediate node or router decides where to send the next, where the next node to send the packets to, and so on. Okay? So that is the network layer. Okay? On top of that is the transport layer. Okay? In the TCP/IP case, that's where TCP runs. There are other transport layer protocols we will encounter, like UDP and others. Okay? They all run at the transport layer. That is responsible, that protocol is responsible for end-to-end communication. Okay? Network layer is hop by hop, okay, 1 hop at a time. Where does the packet go next? The transport layer is responsible for end-to-end communication. So it can do things like loss recovery. A packet that was sent is never delivered because the network was congested or the packet got corrupted. Okay? It can do retransmission of that packets, or it can decide what rate to send packets at. Okay? So all of that is actually done at the transport layer. And then you have session and presentation layer. That's really part of the application that essentially set up a session between the 2 nodes or decide how to present the data to the application and so on. Okay? The actual application that you run, which let's say is a browser or a web server, okay, they are essentially at the top of this protocol stack. Okay? They're only essentially deciding what data to send, and they hand it to the protocol stack, which is going to perform all of the processing. Okay? So that's the picture you want to keep in mind. Okay? There are 2 types of protocols, connection-oriented and connection-less. We will talk about TCP, which is connection-oriented, in just a moment. Connection-less protocols will differ until a later time when we talk about streaming and so on, okay? Much later in the course. Okay? So here's an example of a packet that is actually sent over the network as a result of the processing through the protocol stack. Okay? What will happen is if a browser here wants to send a message, let's say to a web server over the other end, it's going to construct a message, is going to hand it to the protocol stack. Is that message is going to traverse down the protocol stack and get processed by each of these layers, and then it'll go over the network, arrive at the other end, it get processed upwards and handed to the application. Okay? So now when this application message actually gets sent on the network, what does that message look like and what are its constituents? That is what is shown here. Okay? This message box here that's the actual message that the application sent. It could have been an HTTP message with the URL encoded in it. That's what a browser is trying to send to a web server. Okay? Now, when that message is handed over to, let's say, the application layer, presentation layer, transport layer, each of them add a bit of information to that packet, which are called headers. Okay? So there you'll have, in the transport layer, you'll have a TCP IP header, or TCP header, excuse me. For a network layer, header is the IP header, and so on and so forth. The data link layer is your Ethernet header on the frame, and so on. So each protocol layer is adding some information onto that packet, and it's sending it down. Okay? That allows the corresponding peer protocol at the other end to know what to do with this message. Okay? So when Ethernet layer at the other end receives the message, is going to look at the header and say, this is what I need to do with it, or this is where I send it to. Similarly, when IP gets the message, it's going to use the information in the header to perform routing, and so on and so forth. Okay? So that's the message that is actually going to go onto the network. When this entire package arrives at the other end, each layer is going to take a look at the message, strip the header, and then hand it to the layer above. Okay? So when eventually it gets to the application, it's just left with the message that was sent, because all the other layers have processed the information and stripped their header out. Okay? All right. With that in mind, let's just talk a little bit about middleware protocols, because the one thing I did not mention in the 2 slides ago was this is what is called an OSI protocol stack. This is the picture of how a network protocol stack is designed, but not every protocol stack has all of those components present in them. Okay? Specifically, in the case of the TCP/IP protocol stack, essentially the stack is going to stop at the transport layer, and then everything else has to be done by the application. So the presentation and session layers are not present in this case. Okay? So you will have the this is the TCP layer, that's the IP layer, the Ethernet layer, physical layer, and then all of these functions have to be performed by the application itself. Okay? This might include things like encryption and so on. Okay? Now, because the application now has the burden of performing a lot of these additional functionality, you can have other layers that you can insert on behalf of the application that sit between the application layer and the transport layer, and they provide useful functionality. Okay? We will call all of these things as middleware. Okay? Middleware is essentially a piece of software that sits in middle. In this case, it's sitting in the middle of the transport, the network protocol stack and the application itself. Okay? And we'll see a number of different middleware protocols as we go and look at various topics in the course. Things like distributed transaction, distributed locking, distributed commit. A lot of these things can be implemented as middleware that sit between the application and the network and the OS itself. Okay? So that's another thing that you want to keep in mind. But for today's class, forget the middleware layer. Okay? We are really going to see how can an application send a message to another peer application or another server application on the other end using 2 mechanisms. One is using sockets, TCP/IP sockets, and the other is using remote procedure calls. Okay? So that's really, and this is by and large how you are going to write code for your labs, because you are going to write distributed applications. You have to write components that communicate. So you'll either have to use sockets or you'll have to use things like RPCs. Okay? Any questions so far? This is the recap I wanted to do before we start talking about RPCs and things of that. Okay, so let's start with socket-based communication. Okay, so essentially, this is how TCP/IP works. So if process A on some machine wants to communicate with process B on another machine, okay, you can use this abstraction called a network socket. Okay? So what each of these 2 processes have to do is they have to create a socket at their ends, and they have to connect these 2 sockets together so that they can communicate using the socket abstraction. Okay? That's the basic idea. I'll show you a picture. Okay, so these are all the calls you can perform using socket libraries. Okay? The main one that you're actually going to use to communicate are the send and the receive. Okay? Send allows you to send a message, which is any arbitrary data over this socket, and receive allows you to receive data over that socket. Okay? Data could be anything. It could be string, text, numeric data, and so on. All of these other calls that you see, those are what you are going to use to essentially establish the socket, okay, at each end. And I'll show you an example of how this is going to work. Okay? So here is a very trivial client and server that are using sockets to communicate. Okay? The top part is the server, the bottom one is the client. Okay? So what you'll see the example that not the example, all the calls that I mentioned on the previous slide are here. Okay? So what the server has to first call the socket call to establish a socket. Okay? This is basically creating a new socket. Okay? And then it's going to bind that socket, which means it's going to connect it to essentially an address. Is going to listen on that socket, which means it will say that now I'm ready to listen. Listen essentially say I'm ready to accept messages or data over this socket. Okay? And then accept allows you to accept a specific connection over the socket. Read or write or send or receive, they're equivalent in this case, allow you to send and receive messages once connection has been established. Okay? So that's the server side, but here is the client side. The client side is much simpler. Client also creates a socket. Okay? Then it essentially uses the connect call to connect to the server using that socket. Okay? This connect call, okay, essentially synchronizes, is called a synchronization point. This essentially allows the sockets at the two endpoints to essentially be paired with one another, so you can use them to communicate. Anything then you send over the one socket is received at the other end, and vice versa. Okay? Sockets are bidirectional in nature. Okay? You can always send and receive messages. It's not unidirectional. All sockets are bidirectional in nature. So essentially, when you write a server application, okay, you in addition to the code for whatever the server is doing, this is how it's going to communicate. Okay? It's going to create a socket, then it's going to perform a couple of additional calls to establish that socket, and then it's going to sit in a while loop where all of this is going to happen. It's going to accept a connection from the client. Okay? In this case, maybe a browser connected to the server to send a request. It's going to accept the connection. Okay? It's going to read whatever came from the client. This is where the request is received. It's process it, send back a response. Okay? And then you can have a loop here where there can be multiple messages that go back and forth between the client and the server, and then you close the connection. Okay? This is essentially a bare bones figure that shows you how to write a very bare bones socket-based client and server. Of course, we haven't actually put the code for the actual application itself. This is just the communication part of the client and the server. Is this clear, what I just said? Okay. Let me now show you Python code that does the same thing. We are going to hand this code out as a lablet. So you will play with this, and then in the actual lab, we are going to use code like this to write real applications that have client and server components in them. Okay? So whatever I showed you pictorially here is present as code here. Okay? So you will see that on the server side, I call the socket call to establish a socket. Okay? This returns to me an identifier that identifies that socket. Okay? So the socket call has some arguments, which at this point you don't really need to worry about. What this is saying is it's a TCP/IP socket as opposed to a UDP socket, which is a different type of socket. Okay? The next thing you will do is you will bind that socket to a address. Okay? So in particular, you're binding that socket. In this case, you will see there's a number here, 80. Okay? That's called the port number. Okay? Every socket actually has an address on that machine that is established. The address is a numeric address. That's the ID of that socket. That's the ID you have to use to communicate. Because there may be many applications that are running. Each of them have an open socket. So if you just send a message to a machine, the OS has to know which of these applications to deliver that message to. You identify the process or the server you want to communicate to, say, I want to send this message to the server that's listening on port number 80. That's the address that the server is listening on that machine. The server has an IP address. That's the address of the machine. And it has a port number, which is the socket address on that machine. Okay? The IP address identifies the machine. The socket port number identifies which of the servers that are running on that machine is this message going to go to. Okay? Port number 80, if you know, is actually the HTTP port. Okay? All web servers listen on port 80. Okay? Lots of the network services that you may have used, they have well-defined addresses, which means if there is a process or that application running, that is the address it's listening to. Okay? A web server by default, you will put on port 80. Of course, you don't have to. You can make it listen on other ports, but that's the default HTTP port number. Okay? So this is a code you should expect to see in a web server. Okay? So bind allows you to take that socket and connect it to an address, okay, or rather a port number. And then you say listen. Listen essentially says now this socket is ready. And now I can, as a server, I am ready to accept messages. Because I'm listening for messages that are coming to this port. Okay? And then you sit in a while loop. Okay? So this is where you will say, I'm going to wait for the next client to send a message. So I'm going to use that accept call to say, I accept the next message that comes. And then there's going to be some processing code that's not shown here. And then there's, of course, going to be a reply. You either use read or write to send messages back and forth to the server. And then you close the connection and accept the next connection. Okay, so that part is not shown here. I'm only showing the socket establishment part.
Question online. How do peer-to-peer communications happen on the socket level?
Okay. How do peer-to-peer communication happen on the socket level? So the socket code that you will use, it does not matter whether it's a client or a server. Okay? Essentially, you should think of them as two processes, A and B, that want to communicate. Okay? Even in the peer-to-peer case, one peer has to essentially run this part of the code, which in this case is labeled the client code, and the other peer has to be waiting for other peers to send it messages. So it will basically, for the purposes of communication, use the server side of the code. Okay? Even though both are peers, they are neither clients or servers in the client-server sense, but the code you will use is not going to be any different. Okay? Here's the client code. Okay? The client, that's the server code. The client code says establish a socket. So this is a socket on the other end. Okay? And then you connect the socket. And here you will basically say, here is the web server I want to connect it to. Okay? And that's the port number I want to connect to. So that allows the client code to connect to that socket. And then subsequently, you would probably send a message which will presumably be an HTTP message. Okay? Because that part is not shown here. Yes, there's a question. Okay, question is, when I say socket, what does it mean? Okay, socket is the abstraction for network communication. Okay, it's similar. Think of it as, if when I say file, what is a file? A file is an abstraction in which I can store data. Okay, that's where how I store, read, write data from a disk. I use the abstraction of a file. Okay, a socket is an abstraction that allows me to send or receive messages. Okay, that's basically sockets are what you use to implement TCP/IP communication. Okay? So to communicate with any process elsewhere on the network, you have to construct a socket and then send a message over that socket. That's essentially how you are going to communicate. Okay? So the socket establishes a channel between two processes to enable communication. Yes, question. What does listen actually do? Okay, listen in this case is just telling the OS that this socket is ready to receive messages. Okay, question, is it a print statement? It's not a print statement. It just tells the OS that it is essentially the first to call the socket and the bind, just prepare the socket. Okay? Once you are ready to receive communicate or start communication, you have to listen. Okay, listen will say, I am ready to receive messages on this port number. Okay? Servers don't initiate the connection, as you can see here. Servers are just waiting for the clients to send them requests. So you listen, you wait for message. So listen says, I'm waiting for messages. Okay? And essentially that's what accept will then accept a message. And it's the client that has to establish the connection and send a request for the server to then do something with it. Okay, yes, question.
Find the time that the server.
Sorry, what's the question?
It is server socket listen. Find the time.
Cost. Question is just 5 the time the server is running for. No. Server is sitting in an infinite loop. All servers, network servers will sit in an infinite loop. They'll just keep waiting for messages, accept message, process message, accept the next message. So they'll just sit in a loop. Okay, that's a parameter to listen, which I forget what it is, but it's not the time that it's not saying listen for 5 seconds or anything. That's not what it is. Okay. All right. Yes. Okay, question is, what does s.connect do? Are you sending a request? Okay. So connect is simply establishing a TCP/IP connection to the server. So in this case, s.connect says connect to the server www.python.org, www.umass.edu. It's a web server. Connect to port number 80 on that web server. The server is listening for messages. So all you've done is you established a connection. No data has been sent yet. Okay? If you look at the previous slide, this part of the code is not yet shown there. The actual data is sent using send or receive or read write. Okay? All you've done is you've done this part. You established the connection. And then in the rest of the processing, you will send a request. You will get a response. That's not shown in that code. But in the code we will give you, you will have the complete code. So you'll see the rest of it. Okay, this was just a snippet that I put here. Any other questions? All right. So let's now look under the hoods a little bit and try to understand how TCP works. How is it actually establishing the connection and so on under the hoods? Okay, because from your perspective, you just need to look at socket code. You don't really need to worry about what is happening when you call socket or accept or connect. Okay, but it's good to understand how things work. So there are two figures here. The first one shows you how standard TCP works. Okay, TCP/IP works, and here you have the y-axis is time. The time is actually going downwards. There's the client and the server. So this is a message diagram that says how are messages going back and forth. Okay? So the way TCP works is to establish a connection, it uses something called a three-way handshake. Okay? There are three actual messages that go over a network between the client and the server before you can send any data. Okay? So essentially, when the server is waiting on an accept and you do a connect, okay? This is where the TCP/IP connection is established using the socket. Under the hoods, this is what's happening when you call connect and accept. The client, as soon as you call connect, is going to send a message called a SYN message to the server. SYN says, I would like to establish a connection. That's really its meaning. SYN stands for synchronize, but effectively the meaning of that message is, I'm a client, I would like to establish a connection. Okay? Okay, the server is going to send a message back after it receives it. Okay, in this case, it's the TCP/IP part of the server, not the application. Okay? Keep that in mind. Okay? Server is going to say, I send a SYN message, and it will send an acknowledge message. So the reverse SYN says that the server wishes to establish a connection in the other direction, okay? Because it is a bidirectional duplex connection. And the acknowledgement says, acknowledgement is simply stacking whatever has been received from the client, saying, I received your SYN message. Okay? In TCP/IP, every message has to be acknowledged so that the other end knows you received it. You don't get an acknowledgement, you will assume it's lost and retransmit. Okay? So to know that the message is received, you will send an ACK. Okay? And so now the client will hear back saying, okay, the server got my SYN and I have a SYN in the other direction. So it's going to send an ACK to the SYN saying, I received your SYN. After these three messages have gone back and forth, okay, the socket is ready for actual data transfer. Okay? So this is what connect and accept will do to establish that connection over a network. Okay? So three messages is essentially what you're going to pay before you start. Okay? So at that point, you can send an actual request. Okay? It could be an HTTP request, any kind of request. The client can send a request. Yeah. If the client intended to send only one request, it can actually close the connection in the forward direction. It doesn't have to, but it can close it. So you can send a fin. Fin says I'm finished, okay, which means I want to tear down the connection. Okay? Now you will get an acknowledgement from the server saying I received your request, I received the fin. Okay? And at some point you'll send back a response after you process that request. Okay? So now you got the response, and then you can send a fin in the reverse direction and ACK to the fin. Okay? So this is called a three-way handshake, where you're establishing the SYN, the reverse SYN, and the ACK. Okay, to establish the connection, and you see there are three messages to tear down the connection: a fin in the forward direction, fin in the backward direction, and an acknowledgement. Okay? So to send one request and get one response, okay, we have sent 9 messages. We as in TCP/IP. That's the overhead of a socket-based communication. Right? So as you can imagine, if the message is small and the response is small, that's an overhead you have to pay over and over again. You'll establish a socket, you'll send a small message, get a reply, tear down the socket, do the next thing. But to do each of those things, you'll have to have 6 additional messages just to establish, tear down the connection. So there have been efforts to make that more efficient. Okay. Here's an example of what is called transactional TCP. It is not actually used, but there are other types of these optimizations that are in use, where you say, let's not have all of these extra messages. The client will send one message and it will piggyback 3 data items in it. It'll send a SYN, it'll send the request, and it'll send a FIN, all in one actual network message. Okay. So the message has 3 parts to it. You send all of that. And so it says, I want to establish a connection. Here's a request. I'm done. Then the server can say, OK, I want to establish a connection. I acknowledge all the things you sent. Here's the answer, and I'm done. And then you send back an acknowledgement. Okay. So you basically collapse that 9 messages that went back and forth for a single request and a response into 3 messages. Okay. This is an example of how you can optimize message exchange. Okay. When we get to this is not used in practice, but when we get to things like how Chrome has tried to optimize TCP/IP over at Google Chrome browser, that is, we will see that it has used similar ideas, but not using TCP. They use UDP. No question there is. Why is transactional TCP not used? Okay, so use any version of a protocol. The protocol has to be installed at both ends. Right? You cannot unilaterally start changing the protocol, because protocols are rules you agreed for communication. It follows that both endpoints have to agree to the same set of rules. Otherwise, you won't know how to interpret a message. Okay? So TCP is most widely used. Every OS supports TCP out of the box. If you want to implement transactional TCP, you have to now update TCP libraries on every machine in the network. Okay? And think of the number of machines or the internet. It's a large number, so never really became popular. Okay? Yes, question. Why is 3-way handshake needed? Okay? 3-way handshake is how TCP works. Okay? This is how you are going to establish a connection, and both endpoints know that you established a connection. Okay? In UDP, you do not have the 3-way handshake. You simply send a message, and then you hope that the message was received, because there is no error checking and things of that sort. So if you want to establish a TCP/IP connection, TCP will cause the 3 messages to establish this connection. So both endpoints know that the connection is live, and then TCP has to then figure out if messages are getting through, do retransmissions, and all of that extra work, which is not shown here. Okay, question is, what happens if act of SYN is lost? Okay. Any of these messages can be lost over the network. Just because you sent a message doesn't mean that it will actually be received. Okay. But what TCP/IP will do is, for every message, there will be a timer. Okay. So if you sent this message number 2, okay, it was a SYN, ACK SYN, okay, it will start a timer saying, I need to receive an acknowledgement within a certain amount of time that says that the message was received. Okay. If that ACK SYN comes back within that timer interval, you're done. You know the message was received. But if the timer expires and you have not received the ACK, you will assume that the original message was lost. You actually don't know if the message is lost or the acknowledgement is lost. But since you have not heard back, you have to assume that the message is lost, and you'll send that message again. Okay? And then you'll wait for that. So the 3-way message handshake can be more messages if there is actual losses and retransmissions. Okay? And that's true for actual requests and responses as well. Once you send the request, if you don't get an ACK, you'll retransmit the request. TCP/IP library will do it for you. You don't have to write application code that's resending messages over and over again. Yep. Yes. Okay. Question is, how is the answer received after the connection is closed? The connection, because this is a 2-way connection. Okay. So what you have done when you send the FIN from the client to the server, the client says, I don't have any more data to send. The server has not closed the connection in the other direction. So it can still send messages. Until it sends its FIN, it can still send more than one message back to the client. Okay. Normally, you would not send this FIN here. You'll wait for your answer and then send the FIN. But it's showing that you don't have to do it in that order. Yeah. So the duplex connection, which is both directions, is closed when the final ACK goes from the client to the server. Okay. But connection closing has two parts. You can close the connection in one direction, then you close it in the other direction. At that point, it's completely closed. Is that clear? You don't really need to know about these details, but this is what you need to know about. But it's good to know how TCP/IP libraries and protocols work under the hood. Okay, so with that, I'm going to talk a little bit about group communication. We'll come back to this later on in this class when we talk about middleware and so on. Okay, so I'm not going to discuss it in detail today, but I just want to mention it here. Okay? So first of all, what is group communication and how does it differ from what a socket-based communication that I talked about? The way you want to think about this is socket-based communication is one-to-one. Okay? Each socket is connected to one other endpoint, and these two endpoints are communicating with each other. It's a client talking to one server. Okay? Now, there may be cases where you may want many-to-one communication, or so rather one-to-many communication. So this is a case where the server wants to send a message to a group of receivers. Okay? Very similar to email. Right? Typically, email is one-to-one, where there is, if you put one recipient, it goes to only that recipient. But if you send to a mailing list, you send one message, but there are many recipients. Okay? Same kind of stuff here. If you use a group address rather than a single machine address, that group address can deliver that message that you sent over that socket to many different recipients. Okay? This is called group communication. It's very useful in many kinds of distributed applications where the server is communicating with a set of client devices and it wants to send the exact same message to all of them. So rather than sending n messages to each one individually, you send one message to a group and they all receive it. Okay? So it's also referred to often as multicast, okay? Which is different from broadcast. Broadcast is that when you send a message, it goes to every machine in the network. Multicast says when you send a message, it goes to a group, okay, which can be some subset of the machines in the network. Okay? Now, there are many issues there that we will look at as to how you decide how to deliver messages in the group. That's called group addressing. How do you ensure atomicity, message ordering, scalability? You may not understand what these issues mean at the moment, which is okay. When we come back to group communication later on, we'll get into the details of all of it. Okay? But the only thing, the reason I mentioned this here is that there's a variant of sockets that allow you to send this to a group. Okay? Each send or receive is happening to a group, or you're receiving from message that was sent to a group. Okay? But by default, it's one-to-one. That's what you will actually use. You will not use group communication, but that feature is available in some cases. Okay. Any other questions here before I move on to the next topic? You had a question? Yes, go ahead. Okay, question is who resolves the group address? So to implement group communication, you need additional network support that says when you send it to a group, something in the network has to figure out who are the members of the group and then make sure the messages are delivered to them. That's typically done in the routing layer. Okay, so I think so in other words, the routers need to have support turned on for group communication. The router does not have support for group communication, it will just ignore the message. Okay. So next part of this class is going to be remote procedure calls. Okay. So remote procedure calls are a different way client and server processes can communicate with one another. Okay. It's a more intuitive way for any of you who have never actually dealt with sockets. Okay. Because as you will see, using remote procedure calls to write client server application is very similar to how you write programs today. Okay. And you don't have to often deal with all the underlying issues of the network, addresses, and so on, as you will see in just a second. It's a very logical way to take your notion of how you write code and extend it to write code for distributed application. Okay. So the goal of remote procedure calls is to make distributed computing look like centralized computing. By what that means is to write distributed application exactly the way you would write some Python code or Java code that's just a single process application. Okay? You can use the similar abstraction and just make your application distributed, which makes it much easier for you to write. Okay? And we'll see the way we are going to do this is we are going to use procedures as a way to automatically enable communication between the client and the server. Okay? And you all know what procedures or functions look like. So it'll be much easier to understand how to write core applications this way. Okay? And we'll talk about a number of issues, which is how are you going to pass parameters, how do you do bindings, semantics. So these are all implementation level issues when you talk about remote procedure. But let me first give you an example or that explains what is a remote procedure. Okay? First of all, as the name remote procedure calls indicates to you, okay, what you are doing is you are invoking a function or a method, okay, and the method is actually remote, which is why it's a remote procedure call, which means the code for that method is actually on some other machine. Okay? So think about how do you write code now. Okay? What the methods you're calling in this world are all going to be local procedures. They are all local to your code. Okay? So you have a main program that calls a function foo. The code for function foo is part of your program. You wrote it, right? In remote procedure calls, you are going to call this function foo, but it just so happens that the code for this function foo lies in another process that's running somewhere else over the network. Okay? But somehow the runtime and the OS allow that code that is residing on some other machine to be invoked exactly the way you are going to call a local procedure. All the parameters are going to be sent over to that process. That process is going to execute that procedure, okay, and send back a return value to you, to your the invoking code. Okay? So that makes remote procedures very similar to local procedures. Just the only thing that has changed is some code for some procedures is part of the process, okay, and code for some of the procedures that you can invoke sit in some other process. Okay? And they just call procedures, and you can now communicate in this manner rather than using sockets for communication. Okay? And here's an example of a client and a server machine where the server machine has implemented the add procedure. Okay? It takes two arguments, it sums them up and sends a return value. Okay? So what you will see is this is a client process. Okay? The client process is simply going to call add ij. This is how you would call a local version of add if you had written that code in this process. Right? Now, as a programmer, this is all you do. You are not going to say this is a remote procedure, here is the machine it is on, this is IP address. A lot of that is not actually written, code is not written for you, but a lot of code will be auto-generated for this program. Okay? And internally, when you call this add, okay, the runtime will figure out this is not a local procedure, this is a remote procedure. So you have to now internally construct a message and send it to that machine and invoke that procedure on that machine. Okay? So you will construct, you as in the runtime, RPC runtime, will construct this message saying that this is an invocation of procedure add. Here are the two values of the arguments. Here's the integer, which is value of I, here's the integer value of j. And you'll see that this message is now going over the network. Okay? It will reach the other end. Okay? And then this is a server machine. It's going to get this message. It'll say, there's a request now to invoke the add procedure. So you will unpack all the arguments. You'll actually invoke add, and the code for add is somewhere here in the process. Okay, you will call that function. It will execute. A return value will be generated, and this process will repeat in reverse. You'll construct that message for the return, send it back, and in the meantime, this add is simply waiting for the procedure to return. Just as when you call a local procedure, you will wait for a return value while it's executing. The same thing is happening here, except that the execution is on some other process elsewhere on the network. Is that clear? Yes. Okay. Question is if there is another local implementation of the add procedure, what is going to happen? Okay, by default, you're not supposed to have two methods in your code that do two different things. Right? If you wrote a normal program, you wouldn't have two implementations of foo. Right? You will have only one because your code will not know which one to call. So you will not have a local version of add and a remote version of add. If you have that, you have to call them two different things. So it's always clear what you're invoking. Okay? Because each method needs to know which code to invoke. No, your code will not compile because you just have two versions of the same function, right? It will clear a conflict. Yes, question. any real world example of RPC. So RPCs are very widely used for all kinds of applications. You will write client server applications that do this. So you can think of a file server. Many kinds of servers actually use RPCs. Any file server, the client is actually talking to a server, to NFS or Samba or all of these. They use RPCs, but it's very widely used as a technique for communication. Okay, we'll talk next time, not today. We'll talk about there are many RPC implementations as well. We'll talk about one that Google made, is called gRPC. That is what is used for lots of Google services as an example, as well as code that others have written. Okay, question is, when is an RPC preferred over a TCP/IP connection? The first thing I want to mention is that this client and server here, they are also using TCP/IP communication. Okay, this message did not go magically over the network. All communication over the internet uses TCP/IP. The only difference is, in this case, the programmer has not written code for TCP/IP connections. Okay, so internally, this code, which I did not introduce to, is called stub code. Okay, this code is auto-generated. The code at the top is what the programmer or a developer that you write. This rest of the code for actual communication is automatically generated. So even in RPCs are implemented on top of sockets. Okay, except that as programmer, you are not dealing with communication at a socket abstraction. You are dealing with communication using procedure abstraction. It's a higher level abstraction. Okay, so you don't need to muck around with, okay, let me construct a socket, let me do listen. All that is actually happening here. So this is how this client is going to send, the stub code is going to send this message to the server. Okay, so it is not like socket communication is not present in RPCs. It's just not implemented by the programmer, except in the previous case, you actually wrote that code and you sent the explicitly messages for the socket and received messages. Okay, so you're just programming at two different levels of abstractions. Okay, in both cases, you are using network communication, but you'd write different types of code for each of these. Yes, question.
So conceptually, it seems like the same thing.
Okay. Question is this look the same as a REST API? Are they two different things? So first of all, RPCs are one layer below things like REST. Okay? REST is essentially using HTTP for communication. Okay? This is not using HTTP. This is basically using, you can write Python code and Java code and simply call procedures that just happen to reside on another machine. So you are programming now using procedures as your abstraction for inter-process communication. Okay? Now, having said that, REST APIs, you can also think as a form of a remote procedure call, but you're using HTTP as your transport. Okay? You're sending RPCs layered on top of HTTP messages. Okay? That's one way to think about it. So REST is essentially HTTP-based RPC is one way you think about it. Okay? But this is actually much lower level. Any other questions here? Okay, so now let's actually get into some of the details of what is happening. So here, first thing is, how are the client and the server interacting with one another when you send an RPC? So all of these calls that you are seeing here, they are essentially going to be synchronous, or what are called blocking calls, which means when the client process called add, it's going to just wait for a reply. Okay? Similar to if you had called a local procedure, you wait for the return value, you're going to wait for the reply. So the client will just wait until the server processes and sends back a reply. Okay? So this is called, also referred to as synchronous RPC or blocking RPCs. Because next time we will see other forms of RPCs where the client does not wait for a reply. Okay, but by default, RPCs will wait for a reply. So this is the timing diagram here. The client is executing. In this case, it will call the add method. Okay, add method is going to invoke on RPC. That's a message over the network. Okay, the server starts executing the add. Okay, the client is blocked, is waiting for add to return. Okay, reply goes back, and the client continues execution. Okay, we will see more complicated versions of this figure next time, but this is just one to keep in mind for synchronous or standard blocking RPCs. Okay, that's the first thing you want to keep in mind. And then here is essentially some additional details that get you some better understanding of how RPCs work. So this is essentially your local or conventional procedure call. If you didn't have RPCs, this is writing code. Okay, what happens when you call a function? Okay, you take its arguments, you put it on a stack. Okay, then you essentially start executing the code of that function. Okay, the function will take the arguments from the stack, process it, okay, produce a return value. The return value is pushed on the stack. The code returns. Okay, this is how any procedure is going to execute. Okay, for any of the languages that you write. So that's what is shown here. So this is the stack. These are other parameters that are already on the stack. That's your stack pointer. When you call a local procedure call, you put all these arguments, you left some space for the return address and return values, and you called the method. Okay? And if that function calls another function, you will push more arguments onto the stack and pop them and so on. Okay? Now, when you call remote procedures, you are not going to use the stack. Okay? Putting the arguments on the stack is useless because the process at the other end has no access to your memory. Is that clear? Yeah, because that's a different process. It will only has access to memory on that machine. It cannot access the stack of some other process on this machine. So when you invoke a remote procedure, all of these things that you would normally put on a stack, you have to pack it into a message and send it as a message to the other end so that the other the server side of this can actually extract the argument. So you're not going to extract arguments from a stack. When you call a remote procedure, they will arrive as a message over the network, and you can then take it from the message that has arrived. Okay? So that's one thing you want to keep in mind. The other thing you want to also keep in mind is what do the arguments mean in a remote procedure call. Okay? If you have a local procedure call, you know that there are two ways to pass arguments. You can do call by value, and you can do call by reference. Okay? What's the difference between the two? Yes.
Call by value, you pass a copy of the call by reference, pass the address.
Okay, that's right. So if you pass arguments by value, okay, let's say you pass an integer I as an argument, you are going to take integer I, make a copy of that integer, and pass that as the argument. Okay, so that's called call by value. If you call by reference and you pass integer I, you pass an address of integer I. So within the called function, you are actually accessing I itself because you have an address, and you can even modify I. Okay? When you call by value, you can't modify the original variable because you made a copy. You can only modify the copy. Okay? So the other way to think about it is call by reference essentially is passing pointers to arguments. Okay? That's one way to think about it. Call by value makes copies and sends it. Okay? Now, again, in remote procedure calls, okay, you can only pass arguments by value. You are not allowed to pass by reference. Okay? The reason is call by reference essentially passes pointers. Okay? If I passed a pointer and sent it off to a remote procedure call, if I dereference the pointer at the other end, okay, you are not going to be able to make any sense of it because a pointer is a memory address. Okay? So if I say I pass I by preference and its memory address is 100, I'm going to actually send 100. Okay? If I dereference 100, it's going to point to address 100 on that machine, which is meaningless. Okay? So you can't really send pointers over a network because pointers are memory addresses. Memory addresses are specific to a machine. Okay? Here you have multiple machines, so you cannot really pass by reference. So this is one difference between local procedure calls and remote procedure calls. In RPCs, typically you will not be allowed to send any arguments by as pointers or call. You do not use call by reference. There are very specific cases where that restriction is relaxed, but by and large, an RPC system of any sort will by default prohibit you from, not prohibit, but it will not use call by reference. It will actually only call by value. And you shouldn't really pass pointers either. Okay? That's one difference. Okay? The other difference that you have to keep in mind when you RPCs is that the client and the server may not actually be homogeneous. They may not be running the same OS. You cannot assume that they run the same platform and so on. Okay? Let's take an example of a web browser and a web server. Okay? Your web browser may be running on your Mac or Windows machine. You cannot assume that the server is also running on the same machine as yours. It could be running on a different platform altogether. Okay? because you cannot make any assumption of what's happening at the other end. So the server or the other process that's running on the other end might be running on a different platform. Okay? This is important issues that you want to consider when you RPCs. Okay? One example difference, which I will come back to here, we'll go back to the other slides. But one important difference is if there are different hardware architectures, okay, this can cause problems. Okay? So one issue really is whether the architecture is big Indian or little Indian. Okay, does anyone know what this means? Yes, you took an OS class, clearly. Yes, go ahead.
So it's the way that is again
Okay. So what big Indian and little Indian means is if you think of an integer, which is essentially a bit representation of an integer, binary representation of an integer, big Indian and little Indian means which is the most significant bit and which is the least significant. Do I read the integer left to right or right to left? Okay? Some architectures say the leftmost bit is the most significant and the rightmost is the least significant. Other hardware architectures are the other way around. Right? So your x86 might use a different binary representation in terms of Indianness than, let's say, an ARM-based Mac. Okay? Now, what does this have to do with RPCs? If I'm just sending an integer as an argument, okay, an integer is just essentially a binary representation that goes over the network. It arrives at the other end. Okay? You don't know how to read it. If you read it in your native format, you are going to essentially get some integer representation. But if the client that sent you was the other one, okay, you will essentially now read the integer backwards and think that some other argument was sent. Is that clear? Okay. So you need both endpoints to agree on how to interpret any data or arguments that are coming over a network, because you cannot assume that the hardware on both ends is identical. Okay. They might be not, and in particular, they might use different binary representation, different hardware representation. So what are we going to do? How do we deal with this problem? Okay? Because you cannot say my code is only going to run, I wrote it on a Mac, it will only run on other Macs. It can't run on anything else. That's one way to solve it, but that's not very useful. Okay? You want your code to be platform independent. So what we are going to do is we are going to use something called an external data representation, or an XDR, where before you construct the message, the RPC message to send over the network, you take your native representation and you convert all of the data to an external data representation. Okay? An external data representation is a pre-agreed to format for communication. So you can assume, for example, you can say my XDR says all data must be sent in big Indian order. It doesn't matter what your native hardware says. When you send data, you have to send it in big Indian. So if you are a little Indian architecture, you have to flip the bits and send them in that order. Okay? So now if all parties agree that XDR means always big Indian, then there is no confusion. If your architecture doesn't match, you know how to take what came and flip the bits and get the actual data that was sent to you. Okay? So you are going to translate all of your data into XDR format and retranslate it back. So essentially, there's a common understanding of how to interpret data that's sent over a network. Is that clear? So you have to do this additional work so that you can deal with hardware heterogeneity. You can't send pointers. So these are all things that you have to do to make sure your code, your RPC code, is going to run on different machines with different platforms and so on. Okay? You may also have to deal with things like, is your integer 32-bit or 64-bit? Okay? As one example, you might have a 32-bit machine that sent an integer, or a 64-bit machine sent it. You have to be able to interpret that across me. So all of these hardware differences have to be dealt with. You use XDR to communicate what is the data you're actually sending. So you attach a meaning to it, not just send some bits. Okay. All right. So let me go back here. So I talked about all of these things. So you have to use XDR representation. Okay. You are going to essentially use the stub code, that's the auto-generated code, to do all of this work for you. Okay. Everything I said are all issues that have to be dealt with by an RPC system, but not by the programmer. Okay. Programmers have this very easy abstraction. You just invoke methods. Okay. The stub code, the auto-generated code, will deal with XDR conversions. It will deal with making sure you're not sending pointers. It will construct socket messages, send them over. All of the heavy lifting done under the hoods. Okay? So it makes it much easier to write this type of code. All right. So that's essentially brings us to client and subcode. So client is going to make a normal procedure call. If it's a remote procedure, it's going to go to stub code that's auto-generated for you, and it's going to construct this message, send it over. The server side is also written as a procedure, but you write the implementation of the procedure on the server side. The stubs take care of packaging the arguments, sending them over. Packaging of the arguments is called as marshalling of arguments. Okay? And unpackaging is called demarshalling. Okay? In the Java world, marshalling is also called serialization. If you heard that term serialization, that's essentially in Java. Serialization is used for other things, but it's also used to package arguments when you send it over RPCs. Okay? So what marshalling and demarshalling do is they can take complex data structures and they will construct a linear byte stream and allow you to reconstruct that data structure. Right? You might have a 3-dimensional array. Okay? Now, when you send that, you have to say, or maybe let's just take 2-dimensional as an example. Are you going to send them row first or column first? Okay? If you want to reconstruct it at the other end, you need to know how the data was sent. You can't just say it's an 8x4 array and just send 32 integers and expect the other end to reconstruct the array. Because you need to know, did you send them row by row, column by column? Okay? So the marshalling rules are going to figure this out and send them in XDR format so that the other end knows how to reconstruct complex data structures like arrays or other types of structures. Okay? So this is all stuff that has to happen under the hood. Okay? Let me show you some more. I think I mentioned all this already. So you talked about XDR. I also talked about pointers. So by default, you're not going to send any pointers. That's going to be prohibited. We'll talk a little bit about some systems that actually do this. They actually support network pointers. Okay? They allow you to dereference pointers where the address can be actually dereferenced on other machines. This is called chasing network pointers. Very few systems do this, but there are some. Okay? So I will mention some of them next time. Okay? And then I also talked about marshalling arguments, which, as I said, in Java world is called serialize and deserialize, which we'll talk about when we do RMIs as well next time. Okay? Any questions here before I talk about other aspects? Okay, question. So I said the stub code takes care of this for you, and the question is who writes the stub code? Okay, I should have mentioned this. So whenever you write your RPC code, okay, you will run that code through an RPC compiler. Okay? And that RPC compiler will look at the RPC code that you wrote, and it will auto-generate the stub code for you. Okay? So essentially, you have to write a spec, which is called an IDL. So this is the spec for my RPC. This is the code I wrote, and then that RPC compiler will generate all of this. Okay? So it's not that there is somebody's already pre-written code. It's generated automatically for each piece of code you write that has RPCs in them. Okay? And every language will have its own RPC compiler, as you will see. Yes. What does the spec contain? We will talk about that in just a few slides. A spec is essentially, think of it as a header file. It basically lists all the RPC calls that you separate out with these arguments and so on, so you know how to construct those messages. Yeah, so it's basically a ideal spec. All right, so that's one aspect. Now, the other aspect is because when you write RPC code, you're not writing any network level code. Okay? So you start running code that has an RPC call. Okay? Then you execute the RPC call. You can say, how is the stub code to know where the server is running? Okay? How do you know the IP address of the server? How do you know what port number it's listing on, and so on? Okay? So clearly, the programmer didn't specify any of this. Somehow the stub code has to figure this out. Okay? So often there are multiple ways to solve this problem. There's of course the explicit way where you have RPC code where the programmer says my server is going to run on this machine. right? And it's going to run on this IP address and this port number, and then you hard code that in the client, and it's easy. The client knows where to connect to. Okay? But often when you write client server code, you don't know where the server code is going to run ahead of time. Think about Apache web server. Okay? The implementers of the Apache web server can't figure out when they wrote the code where the users or the people who deploy web servers, what IP addresses they're going to run them, what port numbers they're going to run. This is not known ahead of time, right? So that's going to be the implementation time detail. Same is true of many RPC things. You'll write the server code, but you won't know where all it is going to run. So you can't hard code the server address into the client. Okay? So the way you will deal with this is through a process called binding, okay? Where the server is essentially going to advertise itself somehow to the client, so that when the client tries to look for the server, it can figure out where the server is running. Okay? So the way you should think about binding is like a directory service. You essentially register yourself with the directory service. So in the previous example, you have a server that provides the add service. Okay? When that server starts up, it can essentially go to bind itself or send a request to the directory service saying, I'm a server that provides the add service. Okay? This is the IP address of my machine. This is my port number. Okay? And when the client starts up, the stub code, when you call add, it has to go to the directory service and say, is there an add service running on the network? Okay? And what port number is it running at? And then you go figure that out, and then you can establish your socket connection, which does need, if you remember, does need the IP address and the port number. Okay? So you are going to use these extra mechanisms to figure out how to connect to a server and so on. Okay? So that process is called binding. Any questions on this? Yeah, I'll show you some example code that does all of that as well. Okay? But let's now talk a little bit about what happens when you are making RPC calls, but messages are going to get lost. Okay? Because RPC communication involves sending RPC calls, invocation requests, getting back return values, and so on. Sometimes messages might got lost over a network. Okay? And if you don't do anything about it, the client might just wait forever waiting for a reply. Okay? So there are two answers to this question. Okay? One is run things over TCP. Okay? If you run your RPC system over TCP/IP, lost messages will be dealt with by TCP/IP. It will figure out that the messages are lost. It will retransmit, but the application code does not have to deal with it. Okay? That's one way you deal with some network issue. Okay? But there are many RPC systems that will run over UDP, which is the sister protocol to TCP/IP, which does not provide loss recovery. Okay? You send a message and it gives you best effort delivery, which means that it will make a best effort to deliver it. Sometimes the message may not get delivered. So in this case, the client stub has to actually have timeout values and retransmit call requests and so on. Okay? So there are those details you got to deal with. But there are many things that can go wrong, not just that the messages get lost. Processes might crash. Okay? So we got to have some answers to how are we going to deal with RPCs in a world where the network messages are getting lost, or the client server or the client might actually crash. Okay? So here is a slide that tells us a little bit about what we can do in different scenarios. Okay? So first is, let's say the client is running. You make an RPC request. Okay? You are unable to locate the server. Either the server has crashed or is not running at all. Okay? So in this case, your RPC call is going to return with an error. Okay? This is not something you are going to encounter in a local procedure call. It's not like you call a local procedure, the procedure has disappeared. Right? That's not a thing, because when you wrote the code, it wouldn't run if there are missing procedures. Okay? But you can have things like this in RPCs. A server is not to be found, so you can't actually invoke the code at all. So your RPC calls might sometimes return with an error, not a valid return value, okay, if you cannot locate the server at all. Okay? Now, your request message might get lost. You call an RPC function. You made a message and it went over the network. It did not reach the server. Okay? In this case, timeout mechanisms will help, where the client can time out saying, I did not receive the reply, so I'm going to resend the message. Okay? So you call that same message. The add function is going back over the network. Okay. Reply might get lost. Same thing. A reply getting lost means the client has not heard, is going to send a request again. Okay. Except that when you do these retransmissions, you got to be careful. Okay. The reason you got to be careful is multiple invocation of the same method might actually have side effects on the server. Okay. Suppose rather than calling the add function, your function is saying, let's say it's a banking application. Just as an example, you say, okay, deposit $10 to this account. That's your RPC message. Okay. You send the message. Okay. The server executed the message, but the reply value got lost. Okay. So you didn't get a reply saying that deposit is successful or something like that. Okay. So the client is going to time out and retransmit. It'll say deposit $10 to this account. Goes back to the server. Okay. Server will re-execute that message, and now you are in an incorrect state because you actually executed that message twice. Okay. Even though it was the same call. Okay. So this requires a property called idempotency. The idempotency says no matter how many times you execute the message, the end result should be the same. If I say deposit $10 to the account, that same request goes twice, it should not actually make the deposit twice. Okay. It should execute it and send back a reply without changing the state and getting into an incorrect state. Okay. So you have these kinds of problems because of repeated executions that you have to actually deal with at a runtime level. Okay. So if you have your RPC system being idempotent, you're not going to have this problem. Okay. The way you're typically going to deal with that is every RPC request is going to go with an ID. Okay. So if you actually, so then at the server side, you're going to track what requests were received recently, what were the IDs. So if I receive another request, I first have to see, have I executed that request with that ID already? Okay. And I should cache the response so that if I have already executed it, I just take the return value cached and send it, not actually execute it. Okay. So this way, you are going to ensure idempotency and not cause problems. Of course, if you haven't received it, then you execute it. Okay. But you have to deal with all these subtleties because this is a distributed system. It runs over a network where the network is not reliable. Okay. You can have server failure in the middle of execution. That can also happen. Okay. Server is executing a message, just crashes. Okay. Client is not going to receive a response. Okay. And maybe the server recovers after a while, the client resends that request, and you get a value, okay, back from the server. Okay. So the question from a client's perspective is, when you actually get a return value to the RPC request you send, what is it that you can assume has successfully happened at the server? Okay. So you can have what is called at least one semantics. That's a default that says if I sent an RPC, I got a reply, I'm guaranteed that the procedure executed at least once. Okay. If I retransmitted that message and idempotency is not guaranteed, of course, the procedure may have executed multiple times, but at least once is once or more. Okay. At most one says at most, that's exactly what it means, that it executed 0 times or once. Okay. So you will either get an error value or get a valid value. No guarantee says I don't tell you anything about how the system behaves. It's not what you want, but that can be an option for an RPC system. And what you really want is exactly once. That is idempotency, saying no matter how many times I retransmit, if it's the same call I'm sending over and over again, I get a return value. Okay. No matter how many times I send it, it has executed exactly once. Okay. That will ensure automatically idempotency. You don't have to do extra work. Okay. So when you design your RPC system, you need to describe to the developer saying if you write code and you get a successful execution, what should you assume has happened on the server? And you can have at least once, at most once, exactly once, all of these different possibilities. Yes, question.
I make an RPC call with a missing parameter. So do I get a compilation error on the client side, or still the stuff gets sent to the server and the server returns?
Okay. Can you repeat the question again? If I got RPC, what?
With a missing parameter.
Ah.
Where does the error?
So if you write code where you are making an RPC call with a missing parameter, the code will not compile. This is the same as if you wrote a local procedure, you declared the procedure's arguments, and you just have 2 instead of 3. Your compiler, if you have compiled language, will say that there is an error. right? It's not accurate. So you will not actually get the code to run at all. How does the compiler know what is the method? So basically, you have to declare the method. Just as when you write code, you have the declaration of the arguments that you pass to a function, what is the return value. You have to declare all of that. So you have to check that the code actually conforms to the spec of what each of the arguments are and so on. Okay, questions. Functions are in different machine, but the thing you want to keep in mind, if you're calling a remote procedure call on the client, you at least need to know what the arguments that you have to pass, and that has to be told to the compiler. That is where you're going to give that spec to compilers on both ends, right? So you have to at least agree on what are the names of the procedure, arguments, and so on. Okay, yes. Okay. Question is, does this work for TCP/IP or UDP? RPC systems, actually, most of them can run on TCP/IP or UDP. Okay? Some now run on TCP by default, but many systems can run on either one. Okay? Okay. Question: how do you deal with loss recovery on UDP? If you have RPCs that run on UDP, the stub code has to write extra code to have timeouts. If it's running on TCP, you assume TCP will time out, so you don't write that in the stub code. Okay? All right, we ran out of time, so we'll continue this next time. Okay, so.